Hey everyone, we're back with the two-sample t-test. Okay, so we're going to look at independent samples t-test. There are two samples. And what's the difference here? Okay, so it's very, very similar. But before we go into that, let's talk about what the problems with the z statistic were, right? The traditional bell curve, right? It was brittle and we needed larger sample sizes to get reasonable accuracy. And what William Seeley Gossett did, right? He worked for the Guinness Brewery in Dublin, Ireland, and he developed a series of curves, okay? And the red one is for smaller sample sizes, and you see the curves getting taller, right? Why? As the sample size gets bigger. Degrees of freedom, as we learned last time, degrees of freedom is n minus 1. So as the sample size increases, the the peak of the curve, the t distribution gets taller, right? But the width is actually decreasing. I guess I have those arrows drawn in the wrong direction. The width is decreasing, the height is increasing. We have these series of curves, and what do? They, as n goes to infinity, as the sample size increases, their limit is the bell curve, the original bell curve. Okay? So this series of curves turns out to be much more helpful and much more robust as a statistic than the original z distribution or the normal distribution. Okay, so that's what we're talking about. And we have, like I said, very much the same thing when we use it for two samples, right? We're going to do the same data checks. We're going to check for box plots, right? We're going to do both samples, a box plot for both samples. And if n is greater than or equal to 40, we may have outliers. If n is 39 or less, we cannot have outliers. And our density plots, we're going to check both samples for evidence that they were drawn from bell-shaped distributions, from approximately normal distributions. Notice about the sample size here, though. Right? We have two groups, and the sample size for group 1 is n sub 1. The sample size for group 2 is n sub 2. And what we're talking about here is the overall sample size. Okay, n here refers to the overall sample size. All right, so our data checks are what you'd expect, except with the homogeneity of the variances, right? We're going to require that the sample sizes of these two groups have a difference of no more than 2 to 1. The largest is no more than twice as big as the smaller sample. Why is this? Well, again, we can, the t-test is robust enough to handle the lack, having different standard deviations, as long as the sample sizes are not sharply unequal. If the sample sizes are more, if the ratio of the sample size is more than 2 to 1, right, that's sharply unequal sample sizes, and that can cause problems. Okay, so we're going to require that the larger sample is no more than twice as big as the smaller. Okay, so that's all there is. And I'm sorry, I had copy pasted some slides in um, from the previous slide. That's fine. We'll jump over and do the worked examples in the notebook. Okay, so the notebook again covers much of the material that I just mentioned, including how to do the data checks. And our first example is narcissism versus biological sex, male or female. So we're going to ask, is there a difference in the narcissism levels between biological males and biological females at the 0.01 level of significance? So notice we aren't using the standard alpha, we're using an alpha of 0.01. Okay, and they provide the data frame and the subsetting so that we have n underscore m underscore narc and f underscore narc, and those are our subsets. Okay, so before we get started, let's go ahead and set up our hypothesis. our hypothesis, sorry, 3 hashtags to get a third level heading, hypothesis, and the $ notation is underscore 0 colon mu, and I'm going to do it this way, mu subscript f equals mu subscript m. Why are the backslashes there? The backslashes are to let the $ mathematics equation editor know that's a Greek letter mu. Okay, so it's not the text mu mu underscore f. It's the Greek letter mu with a subscript f or m. And then I'm going to copy paste because the alternative hypothesis is very, very similar. The alternative hypothesis, H sub A, is that there's a difference. Okay, now by the way, I'm going to do NEQ for not equal to. NEQ gives me the not equal to inequality, and I have to turn this to markdown. But if the cell is marked down, then these equations will display in the equation editor, the $ mathematics equation editor, also known as LaTeX. Okay. So what does this mean? This means that we're doing a two-tailed hypothesis. Okay, so before, when we were doing these directional hypotheses, right, we found T star, right, T star, and we drew a vertical line and we shaded beyond it, right? Why? Because the p-value is the probability that the results we would see, if the null hypothesis are true, what's the probability you'd see results that are this extreme or more extreme by random chance alone, right? What's the probability that that would be true? That's what we're calculating. And again, we had a mirror image, right? And if we were checking a less than inequality, we were doing the same thing. We were shading below. And the same thing is true. Here, though, we have a not equal to inequality, and we're shading on both sides. We're shading below, and we're shading above. All right? What does that mean? It means that the p-value for the same T star is double when I'm doing a two-tailed hypothesis. So it is important to know which hypothesis I'm doing, but the same thing is happening whether we do it on one side, on the other side, or on both sides together. This is both sides together. Okay? So, the next thing we'll need to do is our data checks, data verification, and this is why we subset it. Let me jump in and say, am I going to do descriptives? Yes. Give me just a moment to pause the video and do descriptives. Okay, so I went back a couple of sections and I found this, and we will do males narcissism, and this will be the mean of M underscore narc. And again, to find the sample size, we'll do the length of M underscore narc, we'll do the standard deviation of M underscore narc, and we'll do the 5-number summary. Okay, so this is, oh, and I didn't find it, I haven't run this yet. Run this and run it again, and there we go. Okay, and sorry, this data verification I need to put up here. So this is in Markdown. This is just a code block. Sorry, I'm a little OCD, not a lot. I want that to look nice, okay? So I'm doing fnarc, just changing the M's to F, and then and this wasn't right, so let me, like I said, I'm not hugely OCD, but a little. And there we go, boom and boom. So we have the standard descriptives for both of these. And here the mean and the median are fairly close together. Everything looks reasonably decent. Okay. And here, mean of 4 and a median of 3, the mean and median are a little further apart. So is there some skew here? I don't know. The mu down to the minimum is only 3 units. The median up to the max is 8 units. So I don't know. Maybe we will be looking at some outliers to the right, right? We can't tell, but again, nothing else looks particularly suspicious with the descriptives. So why don't we do our graphics, okay? And the first thing we can do is a box plot. And I'm going to do the box plot this way. I'm going to say, all right, box plot is going to be narc tilde sex, comma, and the data frame that we want to point it to is the personality data set. Okay, so even though we have these subsetted data vectors, we can actually do this with a statistical formula. And the nice thing about the statistical formula, I put the numeric variable first and the grouping variable second, right? And then it lays it out this way. So I can see female narcissism scores to the left, male narcissism scores to the right. Are there outliers to the right? No, there is a longer tail. We were noticing that it's from 3 to 11. Right, and to the left, it's only 0 to 3, so 3 units here and 8 units here. Is that skew? Well, it's a little bit of skew, but not enough to cause outliers, or there aren't outliers present. Fortunately, there are no outliers present in either data frame. Okay, so what am I going to do? I am going to work on doing side-by-side box plots. Right, I do layout matrix. And inside the matrix, I do see 1, 1, 1, 2 is fine. 1, 1, 1, 2. What am I going to do? I'm going to tell it number of columns is 2. That's going to put these things side by side. And then I'm going to do the LCW. I forget what this is. It's around 8, but I can't remember the right thing. What do I want to do? I want to do plot density, and I'll do m underscore narc. So I'll do title just so I can tell them apart, right? So main is going to be density plot for the males. Okay, I'm going to do the same thing and copy paste. Why? Because the only thing that changes here is the M changes to an F and the title changes to females. And I did get this right. It is LCM. The LWD line width is what we use on some plots to increase the line width. LCM has to do, I'm sorry, I don't know what this function acronym stands for. I don't know what the LCM stands for. So let's be honest there. Let me try a 9. Why? Well, they're fine, right? 8 or 9 both work. I am seeing a reasonable bell shape, right? You can see a little more of the tail to the right, but there is a tail to the left. We do have, in both of these, we do have what looks to be a second mode emerging, but it's not bimodal data. It's just a little extra data piling up in an area that hasn't created a bimodal graph yet. Again, there is a tail to the right. There is a tail to the left. Sorry, that looks awful. There is a tail to the right. There is a tail to the left. And so both of these graphs are fine. They're evidence on both graphs. There's evidence that these were drawn from bell-shaped distributions. Now, notice this. One thing that's cool about the density plot is that it gives us a sample size. And the thing I'm checking here is a sample size not being greater, the largest to smallest, not being greater than 2 to 1 ratio. Okay, well, double the smallest sample size of 55 would be 110, and 74 is less than 110. Okay, so there is nothing wrong with the sample sizes. They are not sharply unequal. They're not equal at all. We have many more females than we do males, right? But we don't see any problems here. Okay, so let me open it up another markdown cell and say that. So data checks, fine. Let's say so samples are approximately bell-shaped or normal. Let me go to normal. That's samples are approximately normal with no outliers, and the sample and the ratio of sample sizes is less than 2 to 1, which covers everything, right? There might be a little bit of skew to the right here in the females data subgroup. All right, but no, this is good. This is all good for us. So let me just put it in bold. Right, and there we go. The data checks are fine. Okay, so let me open up some cells here to have some room to work before the next example. And what are we doing? We are running this hypothesis up here. We are testing whether there's a difference. Okay, and how does this go? Okay, so the cell, we're going to use t.test again. But what we're going to do is we're going to put in two data vectors, right? So I can use m narc and f underscore narc. And then what? I don't need to put anything in. Why? Because the alternative equals, and I believe it's two-sided. But notice this p-value 0.000216 is the same if I leave this off. Sorry. It got... Right? What am I saying? I'm saying that the default for the t-test is to have a not equal to hypothesis as the alternative hypothesis, right? What I use alternative for is when I have a less than or a greater than in the alternative hypothesis, right? I'm going to let it know. But its alternative hypothesis, when I don't specify anything, is not equal to. Okay, and again, this not equal to 0. If we're doing what it's looking at is the difference between the male narcissism and the female narcissism. If there's no difference in the averages, right, then that would be 0. So it's checking to see if there is a significant difference, which would point to a difference in the averages. Okay. So I want to mention one other thing. This is fine. This is great. I can run the t-test with a statistical formula. Right, I can do t.test narc tilde sex comma data equals pers. And I want to make a couple of points. We get the exact same thing. A look at the p-values, right? The p-value of 0.000216 is the same in both places. Okay. If I scroll down just a touch, you can see that it did them in a different order, it appears. But the mean of one group, I believe that's the females, is 3.945, 3.945. For the males, 5.69, 5.69. Now, when we run them differently, they will almost always be almost identical. Okay, there could be slight differences, but they're unlikely. Okay. Now, why did I do this? Because I need those sub data frames, right? I need that to go that way where I have these data vectors for both of my groups. Why? Because I have to do the density plots. There's no way to do a density plot with a statistical formula. And I just said that. I don't know that that's true. I believe it's true, right? Well, let's try it, right? Let's try plot density. Plot density, and let's see what it'll do. See, and it's saying, hey, I need a data vector. This argument x must be numeric. It's saying that I can't understand, that my function doesn't understand a statistical formula. I need a data vector that's numeric, okay? Which I thought was the case. I don't always get that right. You see the DD there. If I click on the cell and hit DD, it will delete it. Okay. So we've done it two ways, and I don't care which way you do it. For the t-test, it doesn't really matter. Okay, but we have it. And now what? Well, now the reporting out that we can do, what are we going to say? We're going to say because P equals 0.00026162, which is less than, and what alpha did they ask us to do this at? I have to go all the way back up to the question. Oh, they said alpha equals 0.01. Okay, so if alpha equals 0.01 and backslash alpha close with a $sign y, because now this gives me a nice, formula. I've got to get back in here, make it markdown, make it go. All right. And again, I just hit DD there. You can delete a whole cell by hitting DD, which is something to be wary of because you only want to delete the cell when you actually specifically want to delete the cell. But because the p-value is less than alpha, we reject the null. We have evidence for a difference between the average narcissism scores of biological males, females. Okay. Notice that we have evidence of a difference. Okay, that was the hypothesis we ran. We did run a hypothesis test. We did find that there's a significant difference between the two, which is higher. Well, we're lucky that we also ran the descriptives, but the t-test also does a little bit of descriptives for us. So what we can say? We can say that due to the fact that the average narcissism level of the males was about 5.7, and the average for the females was about 3.9, right? We see that males on average had significantly higher narcissism levels. Okay, now this is biological sex, not gender. So, by the way, this is old data. This is 2011, 2012 data. There are more modern ways to deal with biological sex and gender when it comes to this survey kind of data, but the variable that we had was biological sex. That's in the data frame where the data was collected. And here we go. Biological males had significantly higher narcissism levels, right? So we have the birth weights of babies, and so we have smoking moms versus non-smoking moms. Okay, so if they were smoking during pregnancy, they're in the smoke data vector. If they were not smoking during pregnancy, they're in the non vector. Okay, so what are we going to look at? Well, first of all, let's do the hypothesis. And again, you'll get good at this. $H underscore 0 colon, and then I'm going to do mu subscript S equals backslash mu subscript N. $, same thing. I'm going to do a dash and a space. That gets the bullet points. This one is probably easier to copy paste. Change the H sub 0 for the null hypothesis to an H sub A for the alternative hypothesis. And now we've got to see this. They say, did the babies born to moms who smoked during pregnancy weigh less? Weigh less. Okay, so that's a less than. That's a less than inequality. All right. And we'll hit Shift Enter. And if we make this a markdown cell, you see the bullet points and the hypotheses are displaying nicely. Okay, what am I going to do? I'm going to copy paste this for the descriptives, right? So I'm going to start with my data verification process. And that needs to go up here. So it's in a markdown cell. There we go. Oh, but now I need to copy paste this again because I just did copy paste. And there we go. And there we go. And what am I going to do? I need smoke and non, right? So this is going to be smoke, 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 and smoke. What didn't it like? It says that smoke isn't there. Because I'm up above where I need to be. Okay. Sorry. Okay, so this data verification goes down in example 2. Okay, so I'm going to put the data verification in here. And then copy paste. I'm just going to delete this one. Okay. Data verification for smoking moms. Sorry, it's not very easy to be delicate sometimes. We don't have a ton of room. And smoking moms or moms who smoke during pregnancy, there's not a kind way to say it. If you only have a certain number of words. And I'm sorry, you see me flailing around. I was just trying to get everything copy pasted correctly and the titles updated so we can see what's going on. Okay, and we're going to do the same thing, and the smoke will change to non for the non-smoking moms or the moms who did not smoke during pregnancy. So again, I'm not trying to be too mean, but you shouldn't smoke during pregnancy either. So, all right, so what are we seeing? These are non-smoking moms. Let me get this right. So update the titles so we can see what we're looking at. Okay, so the non-smoking moms, their babies weighed on average 123 ounces. Okay, and I have to do the math too. I'm like, wait, 16 ounces per pound, and so I'm trying to divide 123 by 16, and I can't really do that in my head. But double 16 is 32, 32, 64, 96. I'm like, okay, that's 100 ounces is a little more than 6 pounds. So 123 ounces is a little more than 7 pounds. Does that make sense? Yeah, that's what babies weigh, right? So this does, in fact, pass the giggle test. It does make sense. 113, that's a little less than 7 pounds, between 6 and 7 pounds. So yes, these descriptives are making sense. To be the data that they claim to be, right? The data of the birth weights of these babies. All right. So we've gotten there. Then we're going to add some more cells. And I can do box plot. And what am I looking at? My birth.weight with capital B, capital W is my numeric variable. My grouping variable is maternal dot smoker. Again, you can inspect this data set to see if that's right. And the name of this data set is births. Okay. Interesting. Okay. So what's going on? A lot of stuff actually. The first thing we see is that okay, so we have false and true. False is smoke during pregnancy, yes or no. So these are the non-smokers, and the median is lower. The babies weighed less, it appears, on average. If the mom smoked, if the mom did not smoke, the baby's birth weight was higher. Notice we have this single outlier low, which makes sense in that babies get about as big as they get. And the outliers are prematurely born babies, right? Babies who are born before full term and thus weigh significantly less. Look at this. This is a baby that weighs 60 ounces. We're talking about slightly less than 4 pounds. Now, medical technology is amazing when me and people my age were born, probably 60 ounces was not survivable, right? But those babies born these days they do survive. They can often survive. I had a friend in college, and her mom was an obstetrician, and she worked at a NICU, neonatal intensive care unit, and they saved a baby that weighed as little as 12 ounces. It weighed the same amount as a can of Coke. Now, can they always save a 12-ounce baby? No, no, clearly not. But they can do some what would have been considered miraculous, 50 years ago when I was born. These days, so there are some outliers to the left, lower, and the non-smokers had some outliers above. Okay, and what are we going to do? Well, notice that on here, the outliers are balanced. We have some outliers above, some outliers below, and they're reasonably not that extreme. We do have one that starts to get a little more extreme, a few that start to get a little more extreme. Here we only have one, and it's not extreme at all. Oh, and by the way, our sample size is huge. Let's do the density plots because then we get the sample size. Right. Um, let me, okay, so layout, and then we're going to do a matrix, and then we're going to do C parentheses 1, 2. We're going to do ncol equals 2. We're going to do LCM is 8. And we're going to close that parentheses. Then I'm going to do a density plot, right? So plot density and smoke and non are my vectors, data vectors. Smoke, smoky. Okay, smoke. And non. And again, we will just make a title so we can tell them apart. Main equals density plot for smokers. Okay, and then I'm going to copy paste density plot for non-smokers. And I've got some number. Okay, so the C closes here. The matrix closes here. LCM closes here. There was just one parenthesis to be closed. Okay, so I had an extra parenthesis on the end there. So we see the smokers. This is nice. I like this layout where I can see the two density plots together. I can see the labels, smokers, non-smokers. They both look bell-shaped. Okay. Are there a few more outliers? By the way, this is called heavy tails. It has a heavy tail to the left. What does that mean? It means that there's more outliers than we would expect to see in a normal distribution, okay? Is it a huge problem? No. Why? Well, because the sample size, 715, 459. Notice that double the 450 would be 900. So the samples are not do not have a difference of more than 2 to 1 in a ratio, right? The ratio is 7 to 4.5, which is not greater than 2 to 1. Okay. We see a little bit of extra data piling up there. Does it cause a bimodal aspect to this smoker's density plot? No. But we see some extra data there where a second mode could be developing. If we had a larger sample size, or if we did the study again, we might check to see if the same kind of thing happens. At the moment, it doesn't mean anything. It's just something we see. What we're seeing, though, is everything we need to. We have a large enough sample size. Okay, so what is my conclusion here? Let's say this for the data check is okay, right? Why? Okay, a couple of reasons. The density plots show approximately normal data, while there are outliers. Our sample size is, what is 459 plus 715? 459 plus 715. Our sample size is n equals 1174. Thus, due to the robustness of t, right? So this is why we like the t statistic, because for large enough sample sizes, it can hold on to its accuracy even when the assumptions are violated. Okay, now I did mention that we don't have skew in only one direction. We don't have outliers in only one direction. We had outliers on both sides. And we didn't have exactly the same number of outliers on both sides. But along with the robustness of T, the outliers were kind of laying out in a little bit of a balancing pattern that makes them they don't compromise our accuracy as much. Okay, thus, due to the robustness of T, we expect the accuracy of the test to not be compromised. Okay. We don't expect, maybe that's the way I should say it. That makes more sense. We don't expect the accuracy of the test to be compromised. Okay. Also, the ratio of largest to smallest sample size is less than 2 to 1. All right, so all the things, right? We've checked all the things, and do we have a few issues with outliers? Yes, but we have a huge sample size. So am I 100% confident in the accuracy? Well, you just don't understand how robust this t statistic is, and the sample size is enough. Yes, I trust the accuracy. Am I going to make a note of the outliers? Yeah, because that's what we do. We check all the assumptions and try to make sure that if there might be any inaccuracy, that we're expecting it beforehand. Okay, so we've got everything done. And I'm going to run this t-test using the statistical formula. So t.test, boom, okay. And then I can do alternative is, and I think it's less than, we'll check. What I'm curious about is I don't know whether it's doing the non-smokers minus the smokers or the smokers minus the non-smokers. And it switches our t.text, I need test. And the p-value is 1. So what happened here, I got the inequality the wrong way. Okay? The mean in the first group was 123. The mean in the second group was 113. So this is a G. This is a greater than. There we go. Okay. Wow. I'd forgotten that this p-value was so small. Okay. So 2.2 times 10 to the negative 16th. Yeah, it's a positive number, but it is really close to the x-axis, right? So that's really small. And definitely smaller than 0.05, which is, I think, what they said for us to test at. We can scroll up to check. I'm scrolling up to see at the 0.025 level. Still smaller than that. Okay. And what am I going to do? Um, I'm just going to grab the reporting out. Why? Because a lot of it will work for us down here. All right. So reporting out, make it markdown. Because P is, wow. Okay. 2.2. Do backslash times 10 raised to the, and you have to put curly brackets around this, 10 raised to the negative 16 power, because P is 2.2 times 10 to the negative 16th, which is less than 0.025, which equals alpha, we reject the null. We have evidence that the babies born to smoking moms weigh less on average, weigh significantly less, sorry, significantly less on average than do the babies born to non-smoking moms. Okay? And why are we doing this? It's an older data set, and they have other ways to check on the health of the baby now, but basically they're using the weight, the birth weight of the baby as a proxy for the health of the baby, and they're saying, hey, if smoking is a problem and it causes the babies to weigh less, then the babies are less healthy. And is it a perfect proxy? No. Is it a reasonable proxy? Yes. Proxy just means stand-in, right? So it's a reasonable stand-in variable for the health of the baby. And this gives us strong evidence that this gives us, yeah, we're definitely rejecting the null here, and we have evidence, good evidence, that these babies born to smoking moms might be less healthy on average. Okay? So, last one. The United data frame, and we're comparing the Atlanta airport delays to the DFW airport delays. Okay, interesting. And let's do this quickly. Why? Because I'm going to just do my data checks. Plot.density ATL, sorry, ATL. Boom. I've got to run this and then it'll work. That's interesting. We seem to have a skew to the right, which leads me to think that we'll have outliers to the right, but notice that the sample size is 270. Okay. And what are we going to do? We're going to look at the plot density DFW. And they also have a skew to the right, but also look at this sample size. Sorry, I jumped back to the wrong thing. Sample size of 161. So 270 and 161, which is 431, I believe. Okay, so our sample size is not as big as it was last time, but it is a pretty significant, pretty hefty sample size. Okay, and then I'm going to do the box plots. How? Well, I can do the box plots. Actually, I'm going to have to do box plots for each. There's not a good way to do it with statistical formula, so box plot ATL, and box plot DFW. And just what we thought, we're seeing some outliers, and this makes sense. Why? Because airline flights are never early. Well, I guess there are a few of them that are early here. Zero would be on time, right? It's delays that we're looking at. And and so it's easy to be an outlier to the right. It's easy, for whatever. If there's a mechanical problem, if there's a bad storm, something can cause a huge flight delay. And that's happened to a few of these flights. Okay. That was the DFW airport. Sorry, that was the ATL airport. Notice that it's almost identical at the DFW airport. The same thing is true. The outliers are mainly to the right, and we have a large enough sample size, so it's okay. Let's run this test. All right, so t.test ATL, DFW, and let's try alternative equals G. See if we got that right. We got a huge p-value, so I think I got this wrong. Again, it was subtracting in the opposite order. And there we go. The p-value is 0.1293. But what does this mean for our reporting out? Well, we're failing to reject the null, okay, because p is equal to 0.01293, which is greater than 0.05, which is our backslash alpha, right? We fail to reject the null. We have no evidence for a difference in flight delays when the destination is ATL versus DFW. So we're not saying there's no flight delays either place. What we're saying is the flight delays that do exist are about equal. And you saw that red here. I had failed to put the last A in alpha. Okay. So I didn't go through the third time. I didn't go through the whole process with the same exactitude, but I'd show the first two showing every single step in detail. So the third one I did quickly, and let me just say, yes, every step is necessary every time. So if you're doing this on a test or a quiz or a homework, you're going to want to do it more like examples 1 and 2. All right, so we'll be back with a look at the match pairs t-test soon.